Hi, this is Christian Hamilton, and today we'll be covering quantum computation. So as far as what this presentation will be, I would like to cover a few basics that I believe would be great for you to know going into reading my essay, and I will like to use the extra time that I have at the end of this presentation to show you a couple things that I did and a couple of resources that I used when creating this essay, learning about computation, and doing research in general. I believe that you, like me, will find these resources to be extremely fascinating and very fun to work with. So to start off, what is a quantum computer? A quantum computer is any device that uses qubits instead of conventional bits. I will get into what that actually means on the next slide. What advantages do they offer? Quantum computers can be extremely fast at certain types of problems, mainly factoring of large numbers, like Shor's algorithm. They can be fantastic for simulations of certain molecular processes and molecular models. They're also great for physics simulations. All of these things are very costly for processing power and time on conventional supercomputers, but these processes are much quicker and much easier to do on quantum computers. What are their disadvantages? So quantum computers are very fast for larger problems, but also slower than conventional computers at small problems. I cover this, the reason for this on the next slide a little bit, and also a lot more in depth on my essay. Also, disadvantages include the physicality of quantum computers. Quantum computers are currently about the size of 4 fridges put together. And they also require a large, costly facility to run. This means that I will not have a quantum computer in my garage anytime soon, and most other people probably won't either. How it works. So a qubit is any material that can achieve superposition. A basic example that makes this easier to understand is, say you have a coin. You flip the coin, and as it's spinning through the air, it can either be heads or tails. It hasn't chosen, in quotes, what it will land on yet. And then once it hits the ground, it becomes locked into a position of heads or tails. This is essentially the same as a qubit, where a qubit has a state of superposition where it is either 1 or 0, upspin or downspin, at the same time. And then only once it is measured, it actually snaps in or collapses in to the position of one of these values. And then entanglement. Entanglement occurs when you bring 2 qubits in close proximity to each other. Each qubit exhibits a small, weak magnetic field, and these magnetic fields interfere with each other. So what this looks like is, say you align 2 qubits properly, and then you choose the position of one, and then you bring them into entanglement. What this looks like is, if you know what one value is for one qubit, you will know the value of the other qubit. Or for example, if you align one qubit to 1 and the other qubit to 0, in this state of superposition, you don't know what either qubit is, but you know that they are opposites. And this guy does a really great job, better than me, of explaining it, so I'd like to go ahead and share this with you really quick.
A close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a
So at that point, he gets into qubit manipulation. Absolutely fascinating. That being said, in the interest of time, I'm not going to share that part of the video with you. I will include it in my paper, though, because I think it's a fantastic video. Now, to finish up, we'll figure out what it is good for, what are its practical applications. Now, I listed a few of these initially, but there are a couple things that we're already working with. Factoring of large numbers using Shor's algorithm. Now, this is kind of huge, because what this means is that quantum computers might be able to basically break through any encryption walls, or 90% of encryption walls that are up right now on the internet. So banking information, account information, security is all compromised by somebody who has a quantum computer, because quantum computers are able to factor large numbers so quickly. Another potential opportunity for quantum computers is extremely fast communication. Because of the effect of entanglement, say you entangle two qubits and then you separate them, then one person encodes a value on this qubit and the other person can view the value that is encoded and has been snapped in. This has potential for allowing faster than light communication, because this strange property of entanglement means that these two qubits interact simultaneously. Now, challenges. There are a couple companies currently working on creating room temperature quantum computation that is a lot more stable. What this means is that quantum computers will be a lot more readily available to the general public and will be able to be used by more people. This also means they'll be much smaller than they currently are, which really opens up the possibility for quantum computers to be integrated into cell phones, computers, etc. Is this going to happen in the next 10 years? No. Is it going to happen in the next 20 years? Maybe. But this is really just showing that there is a lot of potential for this tech, and there are lots of opportunities for what it can be used for in the near future. So now this next source I'd like to share with you, I'm already going a little bit over on time, but this next source is the really interesting one. And I actually was able to get my hands on some quantum computations hardware and software through IBM. So what you're looking at here, I'll explain this really quick and then I'll wrap up the presentation. So what you're looking at here is IBM's quantum experience. So what this is a access to a quantum computer that is cloud-based. So you can create your algorithms, you can test them, and then you can run them on an actual quantum computer that has 5 qubits, and you can run it and get the results in real time. And it's all free. So I'm also going to provide a link to this in my essay as well. So I'm going to just describe this to you really quick, because for me it was really overwhelming when I first started looking at it. Right here, I'd like to point out, fantastic. Here is the Python interface that you can code in. So this is coding, right, in Python, and this is what this is basically, they mirror each other. And this is how a quantum program looks in Python. So in order to create a quantum program, you can either write it in Python or use the logic gates in the interface. I did a little of both, actually, and I found that this method of coding was really interesting to think about, but in the interest of time, I'll just cover this part in more detail. So what these are here, these are all of the logical operators that you have access to, and the different commands that you can make the system run. These H gates, those basically put these qubits into superposition. Each line on this staff, if you will, each line represents a qubit that you're using. As you can see, I'm not using the top qubit and I'm not using the bottom qubit, I'm only using the middle 2. And what I created here is a very, very simple 2-qubit representation of Grover's algorithm. What this is it's a search algorithm for databases, and it can be a very, very easy visualization is by thinking of 4 playing cards. Say I have 4 playing cards, they're all face down. I know that one of them is a queen, but I don't know which one. Now, because of the nature of superposition of qubits and the way quantum computation works as a whole, a quantum computer would be able to find this card on one process. Whereas, for example, if I were to do this, the probabilities of me finding the right card at the first opportunity would be 1 out of 4, 1 out of 3, 1 out of 2, and then 1 successively if I didn't reach the right card until the end. And I'll explain the results really quick as well. So what we're looking at here is this is the interface where I can actually write the program, and this is also where it simulates the result. I ran this on a quantum computer and the result was exactly the same. The reason being because this is such a small and simple program, the simulation of a quantum computer can come up with the correct answer just fine. So right here, I don't know if you can see, but this sphere and this pin, the sphere represents all the possible outcomes, the probabilities of the outcomes, if you will. Here shows 1, 1, 0. That means that there is and it's one pin, so that means that there's 100% probability for the answer to be 1, 1, 0. Again, 1, 1, 0 over here. This straight line shows that there is a 100% probability for the answer to be 1, 1, 0. So what this means, and this will wrap it up, what this means is that in binary, for example, the way to represent 4 cards would be 0, 0, 0, 1, 1, 1. So sorry, 0, 0, 1, 0, 0, 1, and then 1, 1. And then, so what this is saying is essentially 1, 1 is the 4th position of the card. And this is saying that the algorithm ran, and it immediately determined on one operation that the card, in quotes, was on the 4th position. So, like I said, this has been a fantastic experience getting to know more about this process, being able to actually get hands-on with a real quantum computer. I really enjoyed the whole thing. I actually found access to this quantum computer a little bit late through the semester, so I didn't really have a lot of time to develop the types of problems that I would like to, but I covered a lot of material and experimented with building my own quantum programs. This one I found was the simplest one and also the most stable to use. And obviously I'm not 100% an expert. This is something that I really want to spend more time studying, but I was able to find, I used this specific algorithm, this specific program, because it was easy for me to explain. It's something that I understand, and I really wanted to share it with you in a way that, that I could convey how much I enjoyed it and what, basically what it was all about. Anyway, I went way over, sorry about that. Thank you so much. I hope you have a fantastic break, and thank you for watching.